Okay, good. As per today's seminar, today's speaker is Dr. Atis Yosprakob from Niigata University. We'll talk about exploring quantum tunneling in the real-time past interval with the Lefschetz thimble method. Please start when you're ready.
Yes, yeah. Thank you very much for the invitation to talk about my recent work today. So this talk is based on this paper, which has been recently published on JHEP earlier. And yeah, and this work is in collaboration with Jun Nishimura and Kazuta Sakai. So we have been working really hard on developing the technique and also the understanding of quantum tunneling. So yeah, I'm really happy to be able to give a talk here today. So thank you. And yeah, let me start. Okay, so quantum tunneling, as you know, it is an important concept that appears in a wide range of topics in theoretical physics. For example, obviously, it is very important in explaining false vacuum decay, and it's also play an important role in the theta vacuum physics in field theory. And yeah, it also has some connection with instanton physics and solitons in spin chain system in condensed matter. And it can also be used to explain cosmological first order phase transition and also black holes and information loss paradox. So as you can see here, quantum tunneling is really important. So it is very crucial to try to understand what really happens. Okay. So to understand quantum tunneling, usually in field theory, we usually use the so-called imaginary time formalism, which is, yeah, it is a very standard technique when we try to compute the amplitude. And this technique was popularized by Coleman in 1977. So there are basically three steps. Okay. So the first step is we have to consider the imaginary time instead of real time. So the time t here is minus I times the imaginary time. And when we substitute this t equals to minus I tau here into the action of the part integral, this is actually equivalent to considering the negative of the potential. So basically, we flip the potential. So in the case of the quantum tunneling, we originally have double veil in the typical case, but in the imaginary time we flip, so we get the kind of the double Hue potential instead. And the second step, we send the time of the boundary to infinity. So instead of considering the time evolution with finite interval, we send the time from minus infinity to plus infinity instead. And by doing so, the amplitude of the tunneling can be approximated by the saddle points. And these saddle points, in this case, is called instanton. Okay. So this amplitude gamma here can be approximated by the sum over all instanton configurations n here. And this is the exponential of minus of the instanton action. And this figure here shows what an instanton look like. So xe here, this is a Euclidean position of the particle, and this is supposed to be tau, sorry, but this is the Euclidean time, and the particle at minus infinity is on one of the top of the hill, let's say minus one here, and it stays there until at about 0, it will switch to the other vacuum. And namely, it is going to the other side of the hill. And all of this occur at one instant. So that's why this is called instanton. And yeah, so anyway, what's really important is that even though all of these calculations are done in the imaginary time, but it actually gives the real-time amplitude. And the problem is well defined because the integral has a nice convergence. So this is a very standard technique, and it's very useful. But the problem is when we do the calculation with the imaginary time, the only useful thing is usually just the amplitude, but we cannot really study any kind of dynamics because it's not real time. So yeah, so even though the imaginary time is formalism is convenient, but it prevents us from studying how the tunneling actually occurs in real time. So we need a real-time formalism in order to try to understand tunneling in more detail. But the real-time path integral is very notorious. It is well known that the integral is highly oscillating. So let's say, for example, we have this propagator function of a particle moving from the position x1 to x2 with time interval t. And this can be represented by the path integral like this. So we have the sum over all trajectories with with this boundary condition. The initial is at equals x1 and at time t it is at x2. And we integrate the phase exponential of I times the quantum mechanical action here. And yeah, and this phase is highly oscillating depending on the trajectory. And this is really a problem if we want to perform the integration using the Monte Carlo simulation. And this problem is known as the sign problem. So yeah, this sign problem is actually a very common problem when we try to study many interesting systems in theoretical physics. For example, quantum chromodynamic with finite fermion density, or supersymmetry, or gauge theory with the theta term, and so on. So this is a common numerical problem that then there are many ways to solve this. But yeah, okay. But today I will focus on how this work will be use this Picard-Lefschetz theory. So yeah, okay. So that was an introduction, and so this is the outline of my talk. So next I will discuss the Picard-Lefschetz theory, and after that I will talk about the results of our work, and I will give the summary. So, but by the way, if I'm going too fast or if you have any questions, you can interrupt me at any time. Okay. Okay, so first I will talk about the Picard-Lefschetz theory. So basically, the method that we will use to solve the sign problem is the Lefschetz thimble method. And what is it? So the Picard-Lefschetz theory say that when we have some complex integral that is highly oscillating, this integral can be made non-oscillating using the control deformation technique. So in our case, this is the propagator G with the integral of some complex weight. This is highly oscillating. So we can perform the control deformation of this path integral. So instead of considering the particle moving in the real trajectory, we are considering a complex trajectory instead. This is a complex part. And this action here, instead of depending on the real trajectory, it also depends on the complex trajectory. So in a sense, we modify the complex structure of this integral. Okay. So this is the cartoon that simplified the explanation. So originally we have, this is in case of the one variable integral. Okay. So we have the complex plane and we perform an integration along the real axis originally. But the object that the integrand here have a very highly oscillating phase, and this arrow is indicating the phase of each configuration, and yeah, so this gives a sign problem. But when we perform the control deformation in a very specific way, for example, we consider this control instead, and if we do this in a very clever way, it is possible so that the configuration on this along this contour have the phase aligned in the same direction. So if this is the case, then it is possible to perform the Monte Carlo simulation along this contour without any sign problem. Yeah, and this picture here is a thimble, and yeah, the reason this is called the thimble method is because this contour and the axis looks like a thimble. Yeah. And so to get into
yes. Nice
Yes,
question. So
please.
here T is still clear, or T can be also complex, maybe. I miss.
T can also be complex, but in this case, T is real. Yeah.
Oh, okay,
So
okay.
we want to make the formulation completely in real time. Yes. So we complexify the position instead of the time.
I see.
Yeah.
Thank-
Yes. Thank you. Yeah. So yeah. So to get into more detail of the thimble technique, so we have this let's say we have, so instead of the propagator, we are considering the time evolution instead. So this is the wave function after the time evolution, and we have some part integral of some action here. And so the contour deformation is of this particular integral is defined uh, to be a new contour that is generated from the following flow equation. So we have, let's say we have some configuration on the real axis, and this is the original the configuration on the original contour. And then we solve the flow equation where this sigma here is the fictitious flow time, and we flow this into the complex plane, and then we get the new configuration in the complex plane, and that configuration is what is on the contour, on the new contour. And this flow equation is actually designed in a very specific way so that it has two nice properties. So the first property is that the real part of the action is effective action here can be shown to be increasing along the flow. So let's look at this equation. So we take the derivative of this action with respect to the flow time. And yeah, and using the chain rule, we have ds by dz and dz by d sigma. But dz by d sigma is the complex conjugate of the ds by dz. So this is positive definite. So it means that the change of the action is always positive. So yeah, so because of the real part is increasing along the flow, and if you look at this formula here, integrate of e to the minus s here, it means that the configuration away from the saddles are exponentially suppressed because the action is positive away from the saddle. Okay. Sorry. By the way, the definition of the saddle points is that the derivative of the action is 0. So at the saddle point, it is not exponentially suppressed. Yes. And yeah, the second nice property is that because this change of the action is positive definite, it means that the imaginary part of the action is always 0. So the change is 0. So the imaginary part is not modified along the flow. Yeah. So it means that the fluctuation around the saddles are under control. Okay. So we do not change any phase, the structure of the complex phase along the flow. So this might look confusing, but it can be summarized by this picture.
Can you hear me?
Yes, you have a question? Yes.
Could you go back a slide?
Yeah.
So here is in the original path integral.
Yes.
So S effective correspond to minus IS, right?
Yes, yes. Minus S effective is the same as IS.
So
but it's also includes the initial wave function.
Originally S is real in the real axis.
Yes.
Right. So IS is imaginary.
Yes, correct.
So
this S effective is complex, imaginary.
Yeah,
originally.
I know.
Yeah, yeah.
But so in the second line in this source line, so imaginary part. So you mean the imaginary part of S effective, right?
Yeah, that's right.
So you said it doesn't change. So it means that the imaginary part is given by the original IS.
Yes,
in the
correct.
real axis. In the real axis, is that correct?
Yes, correct.
Okay.
Yeah. Is that okay? Okay.
Yeah. Okay.
Yeah. So it can be summarized by this picture. So originally, on the original contour on the real axis, we have the oscillating action. Okay. But along the for each configuration, we can flow into the complex plane. So let's say this configuration, for example, when it flows into the complex plane, it retains the same phase, the same imaginary part along the flow. This one is also the same, and this one as well along the flow. And however, because of the nature of the flow equation, the configuration. So this one is the configuration that flow to the fixed point, and the one near this configuration is also expanding around the fixed point. So it means that at large flow time, the only this configuration or the one near it that have the similar phase will occupy all the configuration space near the fixed point. And the one away from this configuration will flow further away. And it will not be relevant because of the first property that the configurations away from the center points are exponentially suppressed. Okay. So on the Lefschetz thimble here, basically all the configuration will have the same phase. And if we perform the simulation on this thimble, there will be no sign problem. Okay. So yeah, I hope that this is clear. So as I explained in the previous slide, the integration along the deformed part, which is basically on the thimble here, can be basically, this is the fluctuations around the saddle point. So yeah, because so only the configuration near the fixed point are relevant. So the saddle points are very important. However, not all saddle points are relevant. So yeah, in many theory, there are infinitely many saddle points, but only some of them are on the contour. So we have some relevant saddle points where the configuration are populated, but there are some other irrelevant saddle points. So the question is, in the system that we are interested, that is the real-time quantum tunneling, which saddle points are relevant? So that is a very important question. And yeah, saddle points can be obtained analytically, and this is known in case of the double potential. And it is categorized by this paper by Koike Tanisuki in 2014. And for a given boundary condition of, let's say, initial position xi and final position xf, and also the time interval t, the solution can be obtained uniquely up to some mode numbers, n and m, larger than 0. And so interestingly, even though these boundary conditions, xi and xf and t here, even though all three of these parameters are real, it is possible to obtain some complex trajectories. And so this is an example where initial x is 1 and final x is -1 and time interval is 1. And if we choose the mode number nm to be 2, 1, we get the complex trajectory. So this is a complex plane, and initial position is at 1 here. It moves in the complex plane like this in the spiral case, and then it's crossed the barrier into -1 at the end. So this is some strange trajectory, which is not really contributing to the part integral, but it is a solution. So however, yeah, as I explained earlier, it is not straightforward to determine which trajectory is really relevant to the part integral. But there are some discussions about this. So yeah, so Koike Tanisuki in 2015 suggested that the dominant part integral might be some kind of complex spiral part. Okay. But yeah, so it was earlier suggested that this complex spiral part can be obtained from the analytic continuation of the instanton. from the imaginary time to real time. So if you already forget, instanton is the saddle points of the imaginary time formalism that is well known and is used many times, but that is in imaginary time. So this paper suggests that if we perform weak rotation of this instanton to real time, then maybe we will get the saddle points for the real time path integral. Yeah, and this is what such a complex spiral path look like. So we have a particle sitting at one of the vacuum. It then spiral infinitely, and then it cross the barrier and it spiral in the opposite direction into the other vacuum. And this is such a peculiar trajectory. However, it was shown by I et al. In 2019 that this complex spiral path actually gives a correct tunneling amplitude. So yeah, curiously. So we want to try to perform the simulation and check this explicitly with the Monte Carlo simulation in this work. Okay. So there are some comments about the boundary conditions. So yeah, in the previous work so far, what they have been assuming is they are doing the path integral of the propagator. However, we think that what we need to do is not the path integral of the propagator, but rather the time evolution of the wave function, because you can easily imagine that the tunneling process is really state dependent. It depends on the state of the particle. So in order to see what really happens, we need to specify the states. Either it is an initial state or the final state. So in this case, we said that pre or post selected wave function is really important. So basically, instead of considering this path integral of the propagator, we are considering the integration of the propagator with the initial wave function instead. So this is also a path integral. Yeah, so yeah, as I said, it is therefore more appropriate to study a path integral of the time evolution rather than the propagator itself. And also on the technical side, performing a simulation on the time evolution is actually much easier than performing the simulation on the path integral. On the propagator. So yeah. And yeah, and this is also another important result in our paper, and that is the characterization of quantum tunneling. So quantum tunneling is known to satisfy these properties. So the first is that there is no associated real classical trajectory that describes quantum tunneling. And also the amplitude is exponentially expressed by h bar. So the question is, can we understand this from the point of view of the Picard-Lefschetz theory? So to understand that, we first have to assume that the initial wave function is of this form. So we have the initial wave function to be some position-dependent wave function multiplied by the exponential of IPX over h bar. And P here is the physical momentum. Okay. And then we take the classical limit where it has to be taken in this order. First is taken h bar going to 0, and then we reduce the support of the initial wave function to 0. And yeah, so by taking the h bar going to 0 limit, and if we look at the saddle point equation, it can be basically it's these three equations. So the first equation is essentially the Newton's equation, and the second equation defines the momentum, the initial momentum, and it is equals to p, this parameter p here. And the last equation is specifying the final point. And yeah, so the initial momentum is fixed by this parameter p, but the position is actually bound by the support of the wave function. And this allows for two possibilities. Okay, the first case is if the real solution exists, then that's it. So we don't have the quantum tunneling. But if there is no real solution given these conditions, then we only have complex solutions. So in that case, we have quantum tunneling. So this is the nice way to characterize the quantum tunneling. But yeah, so I would like to also notice that this answer is really important because in the previous, in the literature, in the previous, they used a different answer. They use the wave function to be some Gaussian with the width proportional to h bar. So when we take h bar to 0, the Gaussian is reduced to 0 at the same time at h bar. But when we try to get the saddle point equation for using this answer, you can see that it will not allow for real solutions to exist. So we cannot use this kind of answer to characterize quantum tunneling. And there is another note here that the real saddles actually have the 0 real part as you have noticed already, because the original original action doesn't have real part. I mean, the effective action here doesn't have real part. And because if the saddle is already on the real part, it will not flow anywhere. If the saddle is already on the real axis, it will not flow anywhere. So it will not gain the real part. So it is 0. Okay. But the complex saddle is away from the real axis. So it will gain some positive number. And that is proportional to 1 over h bar. But the amplitude is exponential of minus s. So it is exponentially suppressed in the classical limit. So this behavior satisfies everything that we wanted to satisfy. So this is our statement. So based on the Picard-Lefschetz theory, quantum tunneling can be characterized by the dominance of some complex saddle points. Yeah. Okay. Now I will talk a little bit about the technical detail of the Monte Carlo simulation. So the real-time path integral, as I said, it can be done explicitly using the Monte Carlo sampling. And yeah, so we try to approximate the integral by performing the sampling, dynamically. But previously, the simulation is known to suffer from many problems, technical problems, and they are just recently have been resolved. So one of the problems is the ergodicity problem at the large flow time. But this was solved by if we use the so-called volume formulation developed by Fukuyama and Matsumoto in 2021. And this is related to the tempering algorithm. So instead of performing the simulation on the deformed contour only, we allow the configuration to move away from the deformed contour, so that we don't have this kind of trapping problem. Okay, and the second problem is usually it takes a very high computational cost to calculate the force in the hybrid Monte Carlo methods, and we solve that using the newly developed backpropagating Monte Carlo, and this is by our group in last year. And also there is another problem about the divergence problem near the saddle. And this is solved using the optimized, the modified flow equation. And this is planned to be published later. Yeah, so, but using all the, yes, do you have a question? Okay. Yeah, so using all of these newly developed technique, it is now possible to perform a full Monte Carlo simulation of the real-time quantum tunneling. So I will show the result. Before showing the result, I want to talk about the setup first. So this is the explicit setup of the path integral. So we are considering this path integral, which is the time evolution of the wave function. And this wave function depends on the final position and the time interval t. And this is the path integral where we fix the final point of the effective action. And this effective action is depending on two parts. the dynamical part, which is the Lagrangian, and this is imaginary in the original contour. And the other part is the initial wave function. Okay. So this is the integration of the propagator with the initial wave function. But we cannot perform the simulation using this action directly, because this is the continuous degrees of freedom. So this is the discretized version of the action, where we discretize the time into the capital N steps. Yes. So what we are trying to study is the time evolution of some Gaussian wave function in the double wave potential. This is the double wave potential. We have lambda, which is the barrier height, lambda over 2 of x squared minus 1 all square. And this is what the potential looks like. It is a double wave like this. And initially, we have some Gaussian wave function sitting on one of the vacuum. And then we consider time evolution so that this wave function tunnel to the other side. But yeah, so we have to choose the parameter carefully so that the quantum tunneling can be actually observed. So if we don't choose the parameter carefully, it is possible that the setup allows for some classical tunneling, meaning that it is possible to have a particle crossing the barrier because of the high energy and so on. So what we need to do is we have to pick the parameter with this tunneling probability in consideration. So we define P to be the sum over all the energy where or the probability of the particle having energy larger than the barrier. And this should be sufficiently small for the quantum tunneling to occur. And we choose the parameter such that P is of order 0.1. But if P here is too small, then there will be many other problems. But yeah, so 0.1 is a sweet spot. And yeah, and in order to check if our simulation is correct or not, we compute these so-called weak values. Yeah. So as I said earlier, the quantum tunneling is associated with some complex trajectories. And this complex nature of the saddle points can be indirectly probed using this weakly measured trajectory. So maybe you might be familiar with this definition, probably. So we have some initial wave function, and we perform some time evolution at time small t, and then we put the position operator, which is Hermitian, and then we perform another time evolution until the time reach capital T, and then we sandwich with another state xf here. And then we have to normalize by this state. And this is the definition of the weakly measured trajectory, which is complex in general. Okay, but this is in the operator state definition formalism. The same quantity can be defined in the path integral formalism like this. So the right hand side here is basically this is exponential of minus s effective, but we have to add this function here as well, the trajectory xt here, and then we divide it by the partition function, and then we get the same quantity. So it is possible to calculate this directly in the path integral. And yeah, so we obtain this directly from the Monte Carlo simulation, and we cross-check this with the one that is computed from the diagonalization directly. And by the way, even though this weakly measured trajectory is complex, but it can be observed experimentally. For example, by considering the interference pattern in the weak measurements. So yeah, so this is a physical quantity that can be observed directly. And also another important object that we can observe is the saddle points. So the saddle points in the Monte Carlo simulation here can be observed by looking at the typical trajectory that we sample at the large flow time. And the reason is because, as I explained earlier, the configurations are localized at the saddle at large flow time. So it is populating around these saddle points. So if we look at the typical trajectory, this is, yeah, it is the one that is close to the saddle. Yeah. And this is an example of the typical trajectories associated with quantum tunneling. And these are just two of many. There are many trajectories, many possible trajectories, but I only picked two typical trajectories. And yeah, this is a complex plane, and the red line here is the location of the potential barrier. On the left-hand side is one vacuum, and the right-hand side is another vacuum. And the particles start on the left-hand side at t equal to 0, and we allow the time evolution with time interval 2, and the endpoint is here, t equals 2. So you can see that in these two typical trajectories, the trajectories are complex. And the reason that the initial point here is complex is because the initial point is bound by the initial wave function, and it is flow into the complex plane because of the flow equation. So that's why the initial point is complex. But the endpoint is fixed to be some constant 1. So it is fixed even though we flow with the flow equation. Yeah. So another thing that is very interesting is that before the particle cross the barrier, it is in the complex plane. But after it crosses the barrier, it becomes mostly real. And this is the weak value of this simulation here. We compute the weak value as well. And the dashed line here is the one that we compute using direct diagonalization. And the data point here is the one that is computed using the Monte Carlo simulation. So the agreement is good. And this is the weakly measured trajectory on the complex plane. So note that the trajectory of the weak value is not the same as these typical trajectories, and that is because we perform the average of typical trajectories, but with the complex phase. So this complex phase also modifies some complex structure of the trajectories. So they are not necessarily the same. In general, they are not necessarily the same.
Oh, sorry.
Yes.
So, yeah. For example, in the next slide where we was like, yeah, here. What is the dash line here?
Sorry, can you say again?
What's the dash line here in the point?
The dash. Oh, yes, that's a very good question. Sorry. These dash line are the classical trajectory that is. Sorry. Yeah, that is computed using well, as I said earlier, the saddle point for the double wave potential can be obtained analytically. Yes, and this.
Oh, I see.
Yeah, and this dash line here is the analytical saddle point that is very close, the closest to our obtained trajectory. Yes. So the point of this dash line is to show that these are actually the saddles. It's not some random trajectory that we obtain from the simulation. Is it okay?
Okay, thank you.
Yeah. Thank you for asking this question. Okay. So this is another setup where we introduce the initial momentum to the particle. So basically, when we introduce initial momentum p to be -2, we kick the particle to the left initially. And by doing this, we also increase the energy level as well. And by doing that, the process now allows the particle to cross the barrier classically. Namely, it can climb the barrier classically. And this is the typical trajectory. So it starts from somewhere on the left-hand side, it's kicked to the left, but then it crossed the barrier without going on a detour in the complex plane. So compared to this one, this is very large. So it's going far away into the complex plane, but here it's very close to the real line. And this is expected because of the energy level is increasing. And this is the weak value for the trajectory, which is become more real as expected. And another setup that we did was not only we introduced the initial wave function, but we also introduced the final wave function as well. So we post-select the final state. And the post-selected wave function we pick is the we pick the post-selected wave function to be parity symmetric with the initial wave function. So phi x is just the initial wave function with negative parity. And yeah, what is interesting is that both endpoints, the t equals to 0 and t equals 2, are fully complex. Yeah, and another thing is that the trajectories kind of resemble the complex spiral trajectories that was postulated in literature. But the difference is that in the previous literature, they are considering the propagator, and also time interval is infinity. So the trajectory length is infinite here. But here we are considering finite time interval. So it will not be exactly the same. But yeah, interestingly, they have similar behavior. And this is the post-select the how do you say, the typical weakly measured trajectory in case of the post-selection setup. So interestingly, the weak value becomes almost real, even though the typical trajectories are highly complex. And actually, this can happen if the post-selected wave function has a very large overlap with the time evolution of the initial wave function.
Hello?
So if yes.
We have a question?
Oh yes.
Yeah, can you hear me?
Yes, yes.
Okay. Sorry, could you again explain the relation between complex saddle and the tunneling rate?
Complex saddle and the tunneling rate.
How they are related to each other?
Tunneling rate. So sorry, what do you mean by tunneling rate? I mean, how do you define tunneling rate? Because there are many definitions. Okay, maybe you are talking about.
So originally, we all know that the tunneling rate can be calculated by Euclidean method.
Yes. So you're talking about this.
Like this. But now you are studying Lorentzian path integral.
Yes. So okay. Yeah.
And I wonder, so if you can estimate, this kind of gamma in this Lorentzian formulation.
Okay, yeah, that is a very good question. So there are a little bit, there are some difference between this kind of tunneling rate and our setup. So this tunneling rate is good for estimating, well, so the setup here is infinite time, right? So, but in our case, it is completely unitary and it's finite time. So maybe the best way to estimate the tunneling rate in this setup is to consider the energy gap between the ground state and the first excited state, right? So the ground state is usually have one peak, and the first excited state is usually the superposition. Sorry. The ground state has maybe two peaks of one particle on the left barrier and the other particle on the right bar. Sorry, I'm speaking very confusingly, but the ground state usually have symmetric wave function Okay, one peak is on the left barrier and the other peak on the right barrier. And the first excited state is anti-symmetric wave function, where the sign of the wave function is flipped on the opposite side. And if we are considering this initial state, the Gaussian, to be a superposition by just adding the first and the first excited state and the ground state together, and then we can approximate that state by this Gaussian, okay? And if we also approximate the state on the other side after the tunneling to be the subtraction of the ground state and the first excited state. So basically, the tunneling time can be approximated by the difference in the energy level between the ground state and the first excited state, right? I mean, the inverse of that energy gap is approximately the tunneling time. And that tunneling time is, well, it can be indirectly related with the tunneling rate. Is that okay?
Sorry, I couldn't understand. So usually,
Yeah.
if there is no tunneling,
Mm-hmm.
so in this potential, in this case, so we have some vacuum.
Yes.
So at -1, okay, and also we have another vacuum at unity, and they are mixed each other by the tunneling. And so that's okay. So, and I want to know how such a picture appears in this Lorentzian time formulation.
Yes, so maybe we can discuss after we finish
maybe.
the talk.
Sorry.
Yeah, okay, yeah, thank you. Okay. Okay, so it's already actually finished the result. So let me summarize the talk. So yeah, so in order to get some detailed information of the dynamics of the quantum tunneling, it is important to consider the real time instead of imaginary time. And yeah, but the real time part integral is highly oscillating and has a vast convergence, but we can make it convergent by considering the Lefschetz thimble method. Okay, and we give a concrete characterization of quantum tunneling based on the dominance of some complex saddle points in the Picard-Lefschetz theory. And also we perform the Monte Carlo simulation directly and successfully identify the relevant saddle points that is associated with the quantum tunneling. And maybe one of the take-home message is that the thimble technique is a very powerful tool for studying real-time dynamics. So yeah, that is the end. Yeah, thank you very much.
Thank you very much for the nice talk. Any question or comment?
Sorry, maybe is Nishimura-san here? Sorry, I cannot see the participant.
Okay, actually, I have some questions.
Yes.
So do you have some results if we have different potential, like we have some gap between two vacuum?
Okay, so if it is not symmetric, right?
Yeah.
We didn't do the simulation in that case yet. Yeah.
I see.
But that will be interesting, certainly. Yeah.
And another question is it also possible to your formalism is basically about the quantum mechanics, right? So is it also possible to use the tunneling in gravity?
Quantum gravity?
Quantum field theory.
Field theory. Yes, possible. Yes. So it will be more complicated because the degrees of freedom will be increasing, but it is possible. Yes. Yeah, and also in higher dimension is also possible. Yeah. So yeah, this quantum mechanic is basically a zero-dimensional field theory, right?
Yeah, that's true.
Yeah.
But in QFT, it's quite hard to for example, calculating the tunneling rates. If I mean, we can only calculate if the theory have the good good symmetry, like for example Euclidean O4 in Euclidean time or something like that. So I mean, just curious if this is your method could be used in QFT, then say we have such a symmetry, or I mean, in any case, you can calculate the dynamics on.
So at the moment, I don't see any obvious obstacle, except for, of course, the computational cost, I think. Yeah.
I see.
Yeah. So maybe
Any
back to your previous question. So you are asking if this technique can be used to estimate the tunneling rate. Well, so maybe one thing that I want to say is that it's not so there are some connection, but it's not really obvious. Yeah, because the time evolution in this case actually, so as you know, the quantum mechanical system, if we let the wave function do the time evolution sufficiently long time, it will come back to the original state, right? Yeah. So the meaning of the tunneling rate is actually different in case of the tunneling rate in the Euclidean formalism. So maybe, yeah, maybe if I have to summarize, it's just that the tunneling rate may be defined to be the inverse time, and where time here is the time interval for the particle, for the wave function to transfer from one vacuum to the other vacuum. Maybe that is the best definition, I think. Yeah.
Any other question? Do you want? I have one more night question. So,
Yes, please.
you said that your method is good to discuss the dynamics during tunneling, right? So how I can interpret the complex position of your case, I mean, as a dynamics?
Interpret. Well, yeah, of course.
I mean, is it okay just?
Yes, it's okay to.
Is it fine if we just see the real part, or that imaginary part have some meaning or not?
Yeah, so of course the particle is not really in a complex position. Yeah.
Yeah, right.
Yeah. However, this complex trajectory is actually has a significance in the sense that it is some real saddle points. I mean, it is not some artifact from the simulation. But yeah, so it has the same significance with as the instanton. Something maybe you can think of it that way. It has a similar significance as the instanton, but in real time instead.
I see. Okay. Any other question? If not, let's thank the speaker again. Thank you very much.
Yes, thank you very much.